Hi, in this video we'll explain Module 1 of our Universe of Algorithms project, which simulates an interstellar mission where a spacecraft must find out route from its point of origin to a destination avoiding obstacles such as black holes, giant stars, and energy-recharged zones. All of this implemented with our recursive backtracking algorithm in Python. The problem consists of the M4N matrix minimum 30 for 13 represented the galactic map. The chip moves mode from its initial position 0, 0 to destination M-1 N-1, avoiding obstacles and managing its energy. The key elements are black holes, blood deposits can only be destroyed with stars. Giant stars allowed adjacent black holes to be destroyed. Wormholes teleport to cheat the another position. Recharge zones multiplying the cheat's energy. Required charge shields require at a minimum energy levels to pass through. The recursive backtracking algorithm iterates different parts, but runs when energy routes out or there is no way out and recurs valid solutions. The cheat modes in four directions: up, down, left, right, presenting the path close to the destination, each and controls and obstacles is use start to destroy black holes or search for alternative routes, and show how the energy and position history is recorded. The system sets the energy and position history to do about infinity loops and optimizes seed shears. The graphical interface developed with Pygame allows you to view the matrix, the solution path, and control the simulation. The controls are R. Solve the problem from scratch. A. Activate and disactivate automatic animation. P. Pause, resume the animation. And arrows left and right switch between alternative solutions. And space is advanced state by state. It's cut. Close the program. Let's look at the example. The sheet starts with 20,000 energy units and moves reach and destination and use stars to destroy blank holes exploring wormholes for load zones and recharge energy and in special areas. If the energy reaches zero, the algorithm backtracks and tries another route. Finally, it finds an optimal solution and displays it in PIN. In summary, this module demonstrates how a recursive backtracking algorithm can solve complex constrained navigation problems. That code is available in our repository for your exploration.
Okay, hello, my name is Juan Manuel Aguirre, and this is our model of complete implementation of deterministic finite automata. Deterministic finite automata for validation of credit cards and curves. First of all, right here, we have the complete description of the automaton with his correct domain, his states, his first state, his final state, and finally his transition matrix. First of all, we have two main methods, which are credit card validation and curve validation. Inside each of one calls the methods cards file validation and, and curve line validation. First of all, the card line validation determines the type of character, for example, digit, space, or hash. It checks the index status and finally verify the semantic validation, and the date. This one is the complete transition matrix for credit card. The matrix defines transition based on the correct states and input character type. For example, in the state Q0, the only choice we have to pass to the second state is with a digit, because the credit cards begin with 4 digits. Later, we have a space to separate the 4 groups of digits, and as you can see, with this strategy we can check all the states for the transition matrix. If we have right here we have the function that manage the errors, checking state for state, which is the error of the chain that we have. And right here we handle special characters for better visualization. The same is for the curve. We have the validation of files. We have the line curve validation too. And with this is the same logic of the credit cards. We verify the final state, the additional semantic validation, and then we have the transition matrix for curve with the same logic of the credit cards. Additionally, we have to validate the semantic of the curve. With this logic, we can assure that the established requirements are being respected. We could validate the date. We could validate the federative entity, and just like with the credit cards, we have the error manage that handle all the possible errors we can encounter in the validation of this specific automaton, which is the curve. Finally, now with this file visualizer AFD, we can watch the transition matrix with a user interface. And finally, right here, we can run the file and call the respective methods to see appropriately the user interface.